Okay, so it also becomes important and helpful that orbital diagrams can be used to express energy in terms of the different n values, L values, and m sub L values of electrons. So we draw these energy diagrams, and the energy diagrams look like this. And what this is each of these lines here, there's one line here, one line here, one there, three there, 5 there. Each of these lines represents an orbital. Each of these lines represents an orbital. This first line here is in an n equal 1, so that represents the first shell. These next two here, these are in the second orbital, so this is our n equals 2. This first, second, and third one here are our n equals 3, and then this is our n equals 4, n equals 4, all right? And we don't have all the 1, 2, 3, 4, 5 right here, right? And this is 5 here. And then also, so these are our n values, but also we can have our L values up here. Now, do you remember what L value is that corresponds to S, the L value that corresponds to S?
No, I don't remember that.
All right, so let's look at that really quick. Remember, we talked about how L values can be expressed in terms of these letters, S, P, D, F. And what we're trying to do here is trying to allow it so that we can talk about N and L values, one with a number and one with a letter, more simply, right? And remember that if it's L equals 0, we can call it an S orbital, L equals 1 a P orbital, L equals 2 a D orbital, and so forth. And that these S, P, D, F, these L values, relate to the shape of the electron, the orbital of the electron. Okay, so in this orbital diagram, this energy diagram here, I have my 1s orbital, my 2s, 3s, 4s, 5s, and we have over here our p subshells. Now remember, L values represent subshells. So in our n are our shells, first shell, second shell. Remember, n equals 2 means we have 2 L values. And our L values are 0 and 1, or S and P. And also, within our subshells, we have our M sub L values. So n equals 1, L equals 0. M sub L can only equal 0, so there's only one possible orbital. But n equals 2, second shell, L equals 1, this is the P subshell, M sub L can equal -1, 0, or +1. All right, so we have 3 orbitals within a 2p subshell. Within this 3D subshell, can you tell how many orbitals we have?
Well, I think I was falling asleep.
Okay, I know this is kind of hard and doesn't sound like it relates to anything, but if you keep paying attention, gradually we'll get it. Okay, each line represents what?
I can't remember.
Each line represents an orbital, or a shape, a region where electrons can reside. Each n value represents a shell, an energy level kind of way to think about it, an energy level, right? Within shells are subshells. So in n equals 2, that shell has 2, same value as n, subshells. N equals 3 has 3 subshells, okay? So these lines represent orbitals. So in a p subshell, you have 3 orbitals.
Okay.
So, as I said, electrons behave like tiny magnets, and they have a spin, and that's the s, m sub s quantum number, and it is either +1/2 or -1/2. And so within each of these orbitals, you can have 2 electrons in each orbital. Each of them have a quantum number of n either equals 1/2 or n equals -1/2. Okay, so what are we learning here?
I'm not sure.
That was a rhetorical question. You don't have to answer all the questions.
Oh, sorry. Well, you can't be mad at me if you ask a question and then I answer it.
Yeah, you're right. You're right. All right. So what we're learning here is if we look at our orbitals, our subshells and shells all on this energy diagram, we learn first of all that 2s is higher in energy than 1s. Can you see that?
Yeah, I can see that.
2p is higher in energy than 2s. Can you see that?
Yeah.
But the orbitals within a 2p subshell are all the same energy, or degenerate is another way of saying they all have the same energy. So if our quantum numbers are 2, right, n equals 2, and our L value, P there, it corresponds to 1, L equals 1, right? Those numbers give us information about the energy. But the M sub L, if the M sub L was equal to -1, it would be here. If M sub L was equal to 0, it would be here. And M sub L would be equal to +1 would be there. But none of those values would be more energetic than the other. All right, so the energy is in the shell value and a little bit in the subshell value. But M sub L equaling 1, 0, or -1 is all degenerate, same amount of energy. M sub S equaling +1/2 and -1/2 are also degenerate, same amount of energy. Okay, so there's what we call the Pauli exclusion principle, which essentially says that a single electron will always have one set of quantum numbers, and that no other electron in that atom will have the same set of quantum numbers. Okay? The electrons can move from place to place, and then their quantum numbers will change, but at any given moment, it can't have any different, or it can't have the same quantum numbers as any other electron. Okay. The electron configuration, then, can be detailed in terms of our quantum numbers. We can write the electron configuration not just for individual individual electrons, but also for all the electrons in an atom. And when we do that, we can then understand more about how why the electrons in the atoms, or why the atoms have the properties that they have. So these two tools that we have, electron configurations and orbital diagrams. Orbital diagrams, this is an example of an orbital diagram. And the electron configuration, we'll show you in a bit here. But these are very helpful tools in understanding how electrons and how atoms behave. Okay? So, what do you think here? Which is not a possible set of quantum numbers?
Let's see. What do you have that one graph where you said what n could be and m? Yeah, that one there. Yeah, bring that up.
All right, so n can be 1 through infinity, right? L can be 0 to all the way up to n minus 1.
Well, then it can't be A.
Okay, not possible. Why not?
Because if n is 3, the only possible values for L would be 2, 1, and 0.
All right, very good. What's the relationship between M sub L and M sub L and L?
Let's see. M sub L can be only as high as positive L and as low as negative L, and all the integers in between.
That's right, all the numbers in between. Okay, very good. So, Hund's rule. Hund's rule is that when we fill electrons, when we put electrons into an orbital diagram, and we'll begin to do that, we always want to fill the lowest energies first, and no orbitals are going to have 2 electrons until all the orbitals in a subshell have 1 electron. That's Hund's rule. Or in other words, if I'm putting electrons into subshells, so now these circles here kind of represent our subshells the way that those lines in the previous orbital diagram did. I can put 2 into one of the subshells. I can put it into one of a P subshell. This is a P subshell, a 2P. I can put 2 like this, 2 like this, or 2 like this, but I can't put 2 in with different spins, and I can't put 2 with different spins in the same orbital until all of the subshells orbitals have at least 1. All right. So let's try to draw an orbital diagram. Let's try to draw an orbital diagram for an atom of nitrogen. Okay. We start off with our energy. This is POT, stands for potential energy, right? And we have our 1s, 2s, 3s, 4s, 5s, 2p, 3p, 4p, 3d, 5s, and 5p. Now, a lot of you are looking at this and probably saying, how do we know to make the orbital diagram look like that? And I'll show you. But essentially, it's following the periodic table. It's following the periodic table. So if we think about what we're doing here when we're writing an orbital drawing an orbital diagram for a given element, we're trying to look at nitrogen here and find out how its electrons are configured, where they're at in terms of their orbitals, subshells, and so forth. Okay? And so if we start with our first 2 electrons in an atom of nitrogen, the first 2 electrons are in the place where hydrogen and helium would have its electrons, right? Hydrogen and helium have 2 electrons, or hydrogen has 1 electron, helium has 2, and those are in the 1s orbital. So following our periodic table here, we can say that hydrogen and helium here are in a 1s. Okay, so we draw, for nitrogen, we write the, sorry about that. We write,
Who's that guy?
that's my son, he was being silly one day. All right, so we write our, we make a list of the electrons in nitrogen, and this is called our electron configuration. So nitrogen has in it 2 of our 1s electrons. So we say 1s2 are the first 2 electrons in nitrogen. Now, these electrons are the same location as hydrogen and helium's electrons are, right? And then we would draw 2 arrows in our 1s orbital right here. The next 2 electrons that fill an atom are lithium and beryllium, because that's the electrons 3 and 4. And n value corresponds to the row, right? So we were in the first row, so that was n value 1. Now we're in the second row, 2. S corresponds to electrons in our first 2 columns here. These are our S block electrons. So lithium and beryllium, 2s2. This block over here corresponds to L equals 1, or our P block. All right. So boron, carbon, nitrogen, those next 3 electrons are N equals 2, right? Still the second row, but we're in the P block, so 2P, and there's 3 electrons, 1, 2, and 3. So this then, 1s2, 2s2, 2p3, corresponds to what we call our electron configuration for the nitrogen, all the electrons location for nitrogen. And after we get that, we fill in our orbital diagram like this. 1s, 2 electrons, 2s, 2 electrons, and 2p, 3 electrons. Again, they're all going to have the same spin, and none of them are going to pair up. That's Hund's rule. Remember that?
Not really.
Well, When you fill a subshell, you don't pair them up. You only give every orbital in a subshell 1 electron first. So you saw as we went from subshell to subshell, or row to row, we increased our energy. So I knew that the first 2 electrons, n equals 1, s, because they're in helium, should kind of be over here for this type of model. There's always a few exceptions, especially hydrogen and helium. S is our L equals 0 block, and then L equals 1, this is our P block, right? So every time we move from a n value, a new row, we increase our energy. And every time we move to a new subshell, S to P, and this block here is our D block, and we'll talk more about that in the future, we also increase the relative energy. Now, the amount of increase, it doesn't matter too much. All this is doing is it's allowing us to get a rough snapshot of the energies. All right, so let's do the same thing. Let's draw an orbital diagram for vanadium. First, we want to get the electron configuration for vanadium. Okay, so vanadium, the electron configuration. Where are the first 2 electrons? So vanadium's right here, element number 23. Okay, so what are the first 2 electrons in an atom of vanadium?
I don't know. What does that mean?
Well, we're talking about filling this atom up as if it's a nucleus. So here, let me use our Bohr model again for a second. We have a nucleus of vanadium, plenty of protons and neutrons, right? And now we're going to begin to put electrons in one at a time and give the quantum numbers for the location of those electrons. So the first 2 go in again to the 1s2. That's hydrogen and helium. The next 2, it's the second row. So what's our n value?
Second row, n equals 2.
That's right. And I have this block. Do you remember what this block is?
Is that the s block?
That's right. It's the s block. So it's 2s, and then how many electrons go into the 2s?
Lithium and beryllium.
That's right. Just those 2. So 2s2. After 1s2 and then 2s2, we have over here, do you remember what this block is?
That's the p block.
That's right. N equals 2 still. We're on the second row here. So n equals 2 to p, whoops, to p. All right. And then we're going all the way to vanadium. So how many electrons do we have here? 1, 2, 3, 4, 5, 6. So 6 electrons in our 2p. All right. And the next electrons, what are their quantum numbers going to be?
You mean sodium and magnesium's electron-like scenario?
That's right. We're filling this atom that's empty, and the next 2 electrons will be similar to sodium and magnesium. What is their n value?
N equals 3?
That's right, because it's the third row, right?
Right. And then it's the S one, right?
That's right, S. How many electrons?
2.
Okay, good. So what is the L value for S?
Oh, I forgot again.
Okay, so let's bring this back up. Our L value for 0, 1, 2, 3 correspond to S, P, D, and F. So L equals 0 for S.
Okay, got it. So N equals 3 for the 3s electrons, and S or L equals 0 when it's S.
Very good. All right, so we just finished 3s2. That's our third row. S is sodium and magnesium. Now we go over here to aluminum to argon, and that's going to be 3 again. And not S, but what?
P.
And how many electrons?
6.
Very good, 3p6. And what's next?
4.
That's right, 4 is our n value, fourth row.
S.
Very good.
2.
Very good, so that's potassium and calcium. Now what's next?
What would you say? What did you say that blue area was?
This is called the D block. This is the D block.
Okay, so 4D3?
Oh, that's very good, but it's not quite right. And the reason is because when you're in the D block, even though you're on the 4th row, this top block here, this top row, has an n value of 3. Okay, it's the first D, and so its n value is 3. N value here is 4, n value here is 5 and 6 for our D block. So it's not 4D, but it's 3D. And then how many electrons in the 3D to get to vanadium?
3.
Very good. 3D3. All right. So here is our orbital diagram. We're going to put electrons into all of these, right? So there's our electron configuration. We're going to put in electrons, fill it all the way up. 3s, 3p, 6 in the 3p, and then only 2 in the 4s, and only 3 in the 3d. You see that?
Yeah, okay. I still don't know why we're doing this.
Well, let me give you a little hint. Okay. Now that we see what vanadium has in terms of electrons, I'll show you something. Vanadium can either have a +3 ion, by losing these 3 electrons, because there's a degree of stability when you have an empty shell. Or it can have a +2 by losing these 2 electrons. Or it can have a +5 by losing these 2 and those 3. So we can see by the subshells how many electrons atoms can either gain or lose. Just like we could look here and know that, oh yes, these atoms can lose 1 electron and these are going to lose 2. We can now have reference using our orbital diagram to the kinds of ions that these atoms will make based on their orbital diagram. Okay? All right, we're getting somewhere.